first off, I wonder if you have any questions about last night.
Well, not last night, but the night before.
Okay. Philip, would you mind closing the door, please?
Number 22 on 5.8. Page 270.
On page 271, number 22. I thought you did that one.
I probably
Yes, with them. What's the back?
Okay. Well, I'll go online and
Yeah. Yeah, we did that one. Any other questions? Yes. We're on page 282, number 8. Page 283.
Hey, bud.
Okay.
I hit my mic. I hit this chair. Or no, never mind.
Okay. And so they're asking you to evaluate this definite integral right here. And so we begin by giving a sketch of the region. And what do you end up with as your sketch? Yeah, that's right. When I sketch this guy, what I get is a region that looks like this. What's that? I'm talking about just the shaded portion.
Okay.
Yep, just the shaded portion. So the next question that I have is, can I evaluate this as an area of a shape that I know and love?
Rectangle.
It's like a rectangle, but it's not exactly a rectangle because of these sloped
Just a rectangle.
tops.
You can do the triangle at the top and then a rectangle.
I could do a triangle plus a rectangle, yes. I sure could. I can divide this up into a triangle and a rectangle, and I could add those two regions together. Good. What else could I do? What else could I do?
Can you do two trapezoids?
I could do two trapezoids. That's exactly right.
Yeah, that's what I've done.
Yep. And then a nice little variation on that, can I could do two rectangles. How?
Oh, you
Move the right part.
Oh, I see. So like sort of just visually flip this guy up to here. Okay. So we have something like this plus this gives me a rectangle. No?
Rotate it, just rotate it. Two main. One small rectangle and one large rectangle.
On the left side, one be small, one be big, and the areas back.
Can you
Or we
just
could just do two
those,
trapezoids.
you know, like you do a rectangle.
I'm sorry, I'm having trouble visualizing that
If
guy.
you do the left side,
Uh-huh.
then that one would be shorter and the one on the right would be taller.
So I take this little triangle and move it
Yeah, basically.
like this. So I end up with this and this. Don't you, Ed? Come show us. So many options.
Not so much.
Oh, I see. That's clever too. So he takes this guy and he does this with it so that he ends up with this and this. Like that. Yeah, that's right. All of these are the same thing. call
do
it
like
ACB.
this like rectangle and like there's like we just there.
As long as you cover all of the area, you're good. So Bethany, you had some options. Yeah, you know what? I like the two trapezoids too. Here's a variant on this. Since my two trapezoids are congruent to each other, I'm going to do just one trapezoid and multiply by 2. And then it should be fairly easy. It's a matter of identifying coordinates now. This point is 1, 1. This point is 2, 0. And therefore my bases of my trapezoid are 2 and 1, and the width is 1. So I have 2 times the average of 2 and 1 times 1, and all that gives me 3. And I'm done.
Oh, the times 2 already.
What's the moral? The moral of the story is do not be afraid to do mathematical surgery on your regions so that they end up with a convenient shape. Yes, sir?
What was the point of like the shapes and stuff?
The point of the shapes is that we can evaluate integrals as areas if we happen to have a shape that we know the area of formula for.
Yeah, I know that because like what I had done was like area of 2 trapezoids.
Yeah.
But what I was saying, like when you have like all these like broken shapes and stuff.
Oh, here?
What was the point of that?
The point was to show how we could take this region
Right.
and represent the area with a bunch of different kinds of shapes. Yep. Whichever one happens to catch your eye. Good. Any other questions? Awesome. I want to talk now about net signed area a little bit. And the idea behind net signed area is this. I want to consider the case where a function is negative on the interval a to b. So that would look something like this. And I want to consider now what the meaning of the integral of f of x dx from a to b is. Well, if I represent the region here, the region is going to be bounded by f of x here, and it's going to be bounded by the x-axis again, and it's going to be bounded by the vertical line to x equals a and x equals b. And we remember that the meaning of the definite integral is the limit as n goes to infinity of the sum from I equals 1 to n of fci times delta xi. And here's the key point. All of these values for fci are less than 0. So that I'm going to be adding up a bunch of negative products right there. What do they mean? If I draw myself a representative rectangle here, here's delta xi, and here's fci, I can see that fci times delta xi is going to have the size, the value of the area, but it's going to be negative because f is less than 0. And when I take and add up a bunch of negative terms, what I'm going to get are terms is a sum whose size is equal to the area of that region, but whose sign is less than 0. So that this guy right here, the integral from a to b of f of x dx, will be the opposite of the area of our region. It comes out as a negative number because of the way that we construct our Riemann sums. Is this a problem? Well, it kind of depends on the question that we're asking. If the question that we're asking is a question about displacement, then we have no problem with negative displacement. What does that mean? simply means that we're going backwards. If, on the other hand, we're interested in the area of the region, we don't want a negative value. We want the opposite of that because you can't actually have a negative area, right? So we're going to call the integral here to be the net signed area of the region. Signed because if my region is below the axis, I get a negative value. If my region is above the axis, I get a positive value. And net because if my region has some of each, plus and minus, then those are going to cancel one another. And they're going to, we say it in accounting, they net out to whichever value we have. If I have more positive than negative, I get a positive. If I have more negative than positive, I get a negative, etc. So to illustrate this, let's consider the integral from -2 to 3 of x dx. What I'd like for all of you to do is to sketch this region and evaluate the integral using the idea of net signed area. Go. Hopefully your region looks like this. And now I think to myself, what shapes can I find here? I can find not just one, but 2 triangles, right? And what is the area of the triangle on the right? It's going to be, we have a height of 3, we have a width of 3, so this is going to be 9/2. Exactly. This guy right here, what's going to be the area of that triangle? The area is going to be 2. It has a height of 2. It has a width of 2. But because this portion is below the axis, I'm going to write in the net signed area as -2, just like that. By the way, I strongly encourage, unless you're sketching graphs like this and writing in the net signed area for each region, because it then makes computations a lot simpler. And so now when I add up here, I'm going to add the 9/2 as a positive, and I'm going to add the 2 as a negative. And what is 9/2 minus 2? 2.5 or 5/2, right? And we're done. Please notice that this is not the total area of the region. The total area of the region is 9/2 plus 2, or 13/2. It is the net signed area of the region. And that would mean something like this. If my velocity is t, and I'm integrating, I'm finding the total displacement from t equals -2 to t equals 3, then my displacement would be 5/2. Because displacement counts forward progress as positive and negative backward progress as negative. Does that make sense to everybody? Yes, sir.
So it's just graphing it and then making the shapes and finding the areas.
Yeah, that's exactly right. That's exactly right.
So what's the units of these being?
Units? Great question. It's going to be the units of the y-axis times the units of the x-axis, because what you're doing is adding up y's times x's. Yes, you may. Now I want to show you something that's kind of cool, and that is that the notion of net signed area can make our lives really, really simple under certain circumstances. So here is a clever use of net signed area. Take a look at this integral right here. We look at it, we think, I have no idea. So then we think, okay, I can sketch the region. And when I sketch the region, I remember that the graph of y equals sine x looks just like this. And I'm going from 0 to pi. And now what do you notice here? Bingo! I have two different regions. One of them is above the axis and one is below the axis. And they have the same exact shape. They have congruent shapes here. So that whatever value this is, later on we'll discover it's positive 2. And whatever value this is, they are equal but opposite. These guys cancel, and I get 0. These aren't exactly halves of circles.
But either way, it would be like that positive one and the negative one, 0.
0. Isn't that cool? Isn't that cool? I love that. Actually, mathematicians everywhere love that because it makes their lives really easy for certain things. Okay? I was about to share a chemistry application with you, but it's too obscure.
Wait, say.
So, have you ever wondered why, like, hydrogen forms molecules H2 and helium just doesn't? Well, the reason for that basically is when you take the hydrogen atoms and you put them together, their orbitals overlap so that you get a substantial amount of overlap, and this is where the electrons now live. And the electrons act as glue to keep them nuclei together. When you put the helium atoms together, their orbitals actually cancel out for exactly this reason right here. And you get zero. You get essentially an anti-orbital in between them, so that there's very little chance of the electrons being found. They tend to be found towards the outsides, and there is no bonding. Yeah, that's all. Good. What I'd like to do with you is to share now how calculators evaluate intervals. And so for this, you're going to need your calculator. Everybody get that out. And we're going to use our calculators to solve a couple of problems here. Let R be the region defined by y equals x cubed, x equals 1, x equals 3, and the x-axis. Find the area of R. I need to begin with what S word?
Sketch.
A sketch. Exactly so. Everybody begin with a sketch. Go. Sketch R. So you should have a sketch that looks like so. we are. And here we are. So that I have this region right here. And on your sketch, it is good practice to have your function and your vertical lines listed like that. So your sketch should pretty much look just like this. If it doesn't look like this, fix it and file out. Now that we have a sketch, next we're going to represent. Specifically, we're going to represent the area as the sum of rectangles with a definite integral. What will my definite integral look like? The S thing, which is
Yeah.
pronounced integral.
Then
Oh, okay.
3 on top, 1 on the bottom,
We pronounce that from 1 to 3.
from 1 to 3.
That's okay.
And then x cubed. Yes.
Good. Notice that this representation is all about the language. So as I fix your language, what I'm doing really is getting you to do it and say it right. And the quicker you say to yourself, okay, I'm going to learn how to do it and say it right, then the happier you'll be. So I represent. Now that I've got this represented, now I'm going to evaluate. And when it comes to evaluation, we've got some options. So I want to see the options that we have so far, and then we're going to add calculator as our next option. When it comes to evaluation, always I have the option of estimating with rectangles. What are the pros and cons of this option?
So a pro is when you're taking the area, you can just do
Right, right. So which means that no matter what shape of region, it's always available to me, right? So this is a very general method. That's a good thing. On the other hand, what are the bad points about estimating with rectangles? It's not very accurate. And what else? What's the other problem with estimating with rectangles? It's a lot of work. Yes, that is a legitimate problem with estimating with rectangles. It is tedious, it's a lot of work, which means there's a lot of room for making a dumb mistake in there somewhere, and it takes up a whole lot of time. Mathematicians are as lazy as the rest of you. We don't want to do a lot of work if we don't have to, right? So we would say it is inefficient. Okay? So estimating with rectangles, on the one hand, we can always do it. On the other hand, once we get an answer, it may not be very good, and the better I want to make it, the less efficient it's going to be. So, all things being equal, we would prefer not to have to estimate with rectangles. Let's take that and put it as the last resort. This is going to be our method of last resort if we can't come up with anything else. All right? What other options do we have? Area formula. Well, on the one hand, well, what are the pros and cons here? What's that? Yes, that is a big con. The area formulas are specific, not general, which means that I can only use them for certain shapes. What 4 shapes have we covered that we can use it for? Rectangles, triangles, trapezoids, and circles. Half circles, quarter circles. All right, so these are very specific. That's a problem for us. On the other hand, what are the advantages? They're very accurate. In fact, they're exact, which is wonderful. What else? One more thing. How efficient are they?
Very.
They're very efficient, that's right. So if I can get away with it, I'm going to do an area formula. Okay. On the recording, we now have like the Star Spangled Banner hummed 3 times. What we would like to do now is to add the calculator as an option. And I'll go ahead and let you know how the calculator does this, and then I'll show you how it works. Actually, let's reverse that. Let's actually get an answer, and then I'll explain how it works. Everybody grab your calculators, and we are going to evaluate the integral from 1 to 3 of x cubed dx in this manner. First of all, you're going to let y1 equal the function that you are integrating, which we call the integrand. We'll let y1 equal the integrand. And now, having done that, you're going to go down to the option that you've probably seen before in the calc menu, second calc. You're going to scroll down to, I think it's option 7, dy dx. Integral of excuse me, not dy dx, integral of f of x dx, just like that. And you're going to hit enter. And when you hit enter, then it's going to ask you for a left bound. And your left bound is going to be your left-hand Flushing boundary, which is 1. And you simply type in 1 and hit enter. And it's going to ask you for a right bound. And your right bound is your upper bound on your integral, which is 3. And you're going to hit enter. And it's going to think for just a second. And it will shade in all the area that we're talking about. And it will give you an exact value. And if I attempt with my super secret dark arts to do the exact value, then you should end up with 80 over 3, which is going to be 16.67.
Yeah.
Okay, see, I say it.
It should, it said upper and lower.
Oh, did it say upper and lower? So it asked for the upper first? It asked for the lower first.
No, lower.
Okay, good. Okay. Oh, yeah, sorry. No, it should be 20 exactly. Right. Good. So how would your work look on the page? Your work would look just like this. You're not going to share any of the calculator stuff that was done here. You're simply going to give the value. And so it would look like this. You would have a sketch, like so, from 1 to 3. You would have a representation of your area. And you would have an exact value. That's it. That's all you have to do. Now, how does it do it? Well,
Will this use this on homework if you want?
yes, you can use this on homework. However, you're going to find that I often give you specific directions to use some other method so that you're well remembered with this. But yes, in general, in the wild, mathematicians very often resort to calculator or equivalent, computer equivalent to do these integrations. Okay. Now, the question you may have is, how does the calculator do this? Well, the calculator doesn't actually know any more than we do at this point about integration. Instead, the calculator is very good at doing tedious jobs quickly. In particular, what the calculator does to do this is it uses a left sum with 100,000 rectangles. And then it does a right sum with another 100,000 rectangles, the same 100,000 rectangles except shifted over by one, and then it averages them. This is how the calculator accomplishes this. Now, knowing this is really important for us, because here we got 20, which is the exact value, but for another function, we might very well get some answer like 14.167253, blah, 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 blah. And so we wonder, how accurate is that? And generally speaking, for well-behaved functions, our answer is going to be accurate to within about 4 decimal places. So this is usually good. To 4 decimal places, yes.
Is it accurate enough to using calculator compared to what we do by hand?
That's a great question. So is it accurate enough? Let's go back to our pros and cons list here. We had estimating with rectangles. Estimating with rectangles was actually very low accuracy, right? And it was also very inefficient. Whereas now with the calculator, if I add in calculator to our list of methods, and I do pros and cons, I would say that the pro is that it's very general. Which is a good thing. It is also very accurate. It is not exact. It's very accurate, but it's not exact. And it is very efficient. It's not quite as efficient as the area formulas, right? Because I have to do a little bit of overhead. But it makes up for that by being very, very general. So a calculator method is slightly inferior to doing area formulas. But in all other ways, it's much, much superior to doing rectangles by hand, isn't it? So there you go. And that's why mathematicians, professional mathematicians, do integrations by computer or calculator on a regular basis. Yes?
So, 2 questions. When we have a quick count, we have some time integration and stuff.
Good.
Are we going to be able to use like a calculator to solve them, or
If I give you specific directions to do that, then yes.
so we just have to know how to solve them?
Yeah, you really have to be able to walk through all 3 of these methods here.
Yeah. All right.
Yep. So unfortunately, like if I give you a region and I say, use a left sum with 4 rectangles to estimate the area of this region, the calculator answer will give you a better estimate of the area of the region, but it will be the wrong answer for that problem. Okay. Good. Calculator, net signed area. Let's do a second problem with our calculators here. The velocity of a particle moving along the x-axis is given by v of t equals sine of t squared for t's between 0 and 4. Find the displacement of the particle during this time, or during this time interval. Okay. Go. represent, evaluate. Make sure you're in radian mode, not degree mode. Otherwise, you're going to have a sad time. Okay. So your sketch should look like this. We have a graph of our velocity. It doesn't need to be amazing. It just needs to look like this. We're going to label our axes, velocity and time. What is the meaning of this? Well, anywhere where the velocity is positive, what is the particle doing? Nope. Which way? It's moving forward, that's right. And anywhere where the velocity is negative, our particle is moving backwards. So that now that I have a sketch here, I can represent that my displacement, I might call that delta x, is going to be the integral from 0 to 4 of the velocity dt. And this represents velocity times time for each time interval added up. Now I have evaluation. What are my choices for evaluation? Well, definitely not an area formula. And definitely not rectangles. So how about calculator? That works for me. And so I'm going to go and do integrate from 0 to 4. And the calculator tells me that this integral is 0.7471. And there it is. Now, often these problems come packaged with units. So let's throw some units in here. Where v is in, what sort of units should I have for velocity? Light years per minute, meters per second, that works. And t is in seconds. When I compute the integral here, let's finish this before you leave. What kind of units am I going to have? I'm multiplying meters per second times seconds. So I should end up with meters as my final answer.
Oh, this divided.
Oh, and then you times, okay.
But anyway, I just had to say, units are